We've got 4 spectra. Where should we start our analysis? Why do we want to start with the IR? Lovely answer for someone that hasn't taken my class before. I appreciate that answer. All right. It'll tell us the bonds that are present. Why does that matter? What's that? Okay, so it gives us information about bonds, yeah, but why start with that? Why not start with HNMR that gives us a whole lot more structural information? It's a pretty straightforward answer. It's easier. It's easier and it's faster. Your interpretation of the IR should go incredibly quickly. Okay? So quick, in fact, that it makes sense just to get that information. What are the primary bonds present down on paper so that you can get credit? If we consider what's going to happen on the exam, there's really 5 things as part of a complete solve. How do you analyze the IR, the mass spec, the HNMR, the carbon NMR, and what's the final answer? Right? If you tell me the IR, I would argue you've covered 20% of that. You get 20% of the points for just analyzing the IR. So that's a pretty sweet thing if it's an easy process to go through and do. The HNMR takes by far the most amount of time, not the best place to start. Even though it gives us the most information, if we make a mistake there, everything could fall apart quickly. Right? So it makes sense to start with the IR. The worksheet, or our organization document, gives us a pretty good hint as to why, or that we should start with it, because the very first thing listed on it is IR. So now what we've got to do is answer that. Okay, so what do we see in the IR? Which one is the IR? Top left is the IR. How do you know that? That's what IR looks like. Well, what are you looking at to say that that's what IR looks like? Right? So we can think about that. Our peaks are all aimed downwards, so these are all peaks, whereas in the other case, all of our peaks are upwards. Right? So that could be a good tip-off. The other thing we could look off is exactly where you referenced to begin with. You said you saw something at 3,000. Do any of our other things have any numbers at 3,000? Okay, no, so we can use the information of our axis, okay, or our axes to help us narrow that down. Okay, so we've got a signal at 3,000. Okay, I would actually argue we don't have a signal at 3,000, okay, but highlighting that 3,000 range becomes really, really important. Because if you're slightly less than 3,000, that means one thing. If you're slightly more than 3,000, that means another. Okay, but that's really hard to see on this particular graph, right? So what we might want to do is come up with a way to ensure that we can actually see that appropriately. The best way I have found is to, on an exam or on this worksheet, is to take a second sheet of paper. The second sheet of paper has a 90-degree angle on it, kind of like this board. And so what you can do is align the base of the board with the bottom axis, and then align the other one with your 3,000. Are the peaks greater than or less than 3,000? Less than. As soon as I now know they're less than, I now have a bit more interpretation that I can drop on this. How many peaks are there that are less than that 3,000? There's 3. How many do I interpret? The whole group. I don't have to care about referencing each of those individual peaks. What I'm referencing is that group of peaks. That group of peaks is now what I'm going to try and do is match that to common peak patterning for the types of bonds. Because what we identified outside of this recording was that IR referenced bonds. Okay? So what kind of bond produces that kind of peak patterning? A CH bond does represent that. Okay, well, what's going on? Well, IR provides light energy, or not light energy, electromagnetic spectrum energy. Ultraviolet and visible does the same thing. It provides electromagnetic energy. In ultraviolet invisible, when we hit a sample with that, that causes an electron to jump energy levels. IR is significantly lower in energy. So low, in fact, it can't even cause an electron to jump energy levels. Then what's the IR doing? Where have you heard IR before? Where have you heard of infrared? Electromagnetic spectrums. You're referencing other parts of the electromagnetic. You've never heard of like infrared goggles? Okay, what do infrared goggles allow you to do?
See heat.
See what?
Heat.
Heat. And how do we get heat? What did we have to do? Friction, which is coming from movement. What's happening with IR? It's a vibration. Our molecule is moving. Okay? And what we're looking at in particular is individual bonds moving. And a bond is composed of two atoms of different masses, depending on the atom they are, and then we have the electron cloud in between them, that sharing. That sharing of an electron cloud changes the strength of the bond. So as a ballpark approximation, what we have is two masses attached by a spring. And if I hit that spring, does that mean the spring vibrates? What if I don't hit it very hard? It doesn't vibrate much. When does it vibrate? When I hit it hard enough to overcome that energy. That's when it vibrates. And if I hit it too hard, it now moves so fast that it can't really vibrate. So what we're looking at within this is scanning a whole, I keep referencing different sides. I think I've moved it to every screen. Okay? What we're looking at with those numbers is the energy that we're firing at it. And when it hits the perfect energy to cause the bond to vibrate, the molecule absorbs it, and we see that now as a peak. If the energy isn't enough to cause the bond to vibrate, what happens? The light passes straight through, which is why we're getting 100% transmittance. Right? So it's just bond vibrations. Well, what things are going to change that? The identity of the atoms. If I had an oxygen and a hydrogen, is that going to change what's happening with the energy of that spring versus a carbon and a hydrogen? Yeah, those are different masses on either end. Right? What else could I do to affect the energy of the bond itself without changing the identity of the atoms? We could talk about the different bonds types within it. We could say if I have just a sigma bond, that's going to be relatively easy to vibrate than if I had a sigma and a pi. That pi reduces that vibration ability. That's going to change the energy around. Cool. Right? The next thing that we could also consider, which is what you suggested and I didn't write down, hybridization. If our atom has changed its hybridization, that's changing the orbitals that are being used to make the bond. If the orbital is being used to make the bond, we're changing the bond strength. Right? And if we're lucky, we can now detect and use that to dictate what type of hybridization we're seeing. So when you said CH, you didn't just say CH, you said CH sp3. You're saying you know the hybridization of the carbon. Why? You've memorized that already from looking at either a table or other structures of CHSP3s to say that's what that signal looks like. Okay? That comes with experience. Okay? Have you seen those little shape things that you give little kids? Like the circle, and there's a circle hole, you put the circle into it. Okay? Apparently you have younger siblings and nobody else does. Okay? But there's a game like that where you have to put the shapes in the different shaped objects. Okay? Is that an easy thing for you to do? Like if I gave that to you and said, this is an assignment for you, you'd think I'm an idiot, right? Okay? Why do we give it to babies if it's so easy?
Because they don't.
Babies don't recognize those shapes, so it takes time for them to learn. We've learned what those shapes are. We needed experience with those shapes. That's why we give them to babies, to get them to learn and figure out those shapes. IR is exactly the same thing. Right? You don't have that experience, at least the vast majority of the class doesn't have that experience yet. So you need to start building it. This means looking at multiple spectra, finding them online, okay, and find them with structures tied to them. So you start getting used to the patterns that go with it. The spec background document has several kind of representative shape patterns that you should be using. They're not perfect. They're representative, and I'm trying to do the best that I can. And if we look within those examples, that's what we're trying to use to help identify these shapes. Make sense? Okay, next part. Cool, you analyze that. Are there other peaks? And that's a common statement. They're not important ones. It's absolutely false. Every peak we see is important. It references a type of bond. All right, so let's lean on it. Why do you think they're not important?
I was taught that way. I don't have an answer.
But you looked at this one. What is different from that one versus different from those?
They are past 1600.
Okay. There's a range that we start to look at. When we look at IR, that's interesting that you said 1600. Okay. Typically, what we would reference is anything 1400 and lower is what's known as the fingerprint. When you go through to talk to someone, okay, to meet someone new, okay, you might ask what shirt they're wearing, what color shirt they're wearing, how tall they are, okay, so that when you meet them, you know who they are roughly, okay? But are you looking at their fingerprint? Their fingerprint identifies them better than that, because if we said black shirt, who are we talking about? There's 3 people with black shirts in here. So maybe we need to use fingerprints to figure that out. Okay, well, the fingerprint is now so nuanced and challenging to look at that it's usually not worth the trouble. It's not that it's not important, it's that there's a ton of information there, and that's effectively information overload. That's why we ignore it. Okay? And we shouldn't just blanket ignore it, because there is useful information in it, but we should really only dig into it if we have to. Okay? There has to be a reason to move into it. Okay? That's our fingerprint. Interestingly, Doobie didn't say 1400. What'd you say? You said 1600. Is that really what you were taught? 16?
I think so, yeah.
Okay, which is fine. That's how I tend to teach it too. Okay? And I would almost argue I even go higher than 1600. Okay? And 1600 and less I tend to ignore as well. Okay? Why? Largely the same reason. Okay? A lot of stuff can show up in that range. It's really easy to overanalyze it. And so where I want to focus in the places that's less challenging or less, it's easier to get a correct absolute answer as opposed to going, is that a carbon-carbon double bond, or is that a carbon-nitrogen double bond, or is that a carbon-oxygen, okay? Or is that actually a triple bond? Okay? Getting really subtle changes in that structure, all of those things can kind of happen in that range, and I want to avoid putting analysis in there, because the instant I write down that analysis, I'm now in the mindset of that must be true, and that isn't always the case. Okay? Kind of makes sense? So within this, if we're going to push all the way to 1600, what is our analysis for the IR? 15 minutes later. Within our first 10 seconds, what we should have acknowledged is that we have a CHSP3, and that was it. Okay? We've got that analysis on our spectra. I would argue that it should go onto the worksheet or our spect.org and away from the spectra. Because if we put all our work on the spectra, there's a bunch of stuff there that we aren't using. We don't need to see all those peaks. What we need to see is the important thing, that it's CHSP3. That's all I care about. The rest of it is noise that could now confuse me later on. So I want to shift away from that space. Kind of make sense? Okay. Which then sets us up with the next one on the list. Okay. And if we look at how I structured these individual worksheets, you might go, well, top to bottom, left to right. So top is IR, the next one to the right must be the one we're looking at. And yeah, I would argue that's a fair assumption to make. Why would I set it up that way? Same way I set it up with the worksheet. For a small amount of work, I can get a lot of information. Right? Whereas if I look at HNMR, the last thing on the list, there's a lot of work that has to go into it. I get a big bang for my buck, and I get a lot of information back out. Okay? But that's a lot of effort I have to put in. So if I look at IR, that just in our talk here took 15 minutes. Okay? That's pretty quick. The vast majority of our time, probably 60 to 90 minutes, is going to be spent in the HNMR. That's a big time investment for that kind of reward. Okay? If we consider points, it's still 20%. Make sense? Okay, so mass spec. What do we get out of mass spec? As a hint, it says mass spec. What's that? Yeah, we get our molecular weight, okay, referencing the mass, okay, which on our worksheet is our grams per mole. This means what we have to find is the M plus peak. What is the M plus peak in a mass spectrum? Okay. It is the peak furthest to the right. Okay, so there's our peak furthest to the right. Then what? Because it's not the peak furthest to the right. That's only half of it. The tallest peak within 3 units of that peak. Okay? Which becomes the fun part, is I'll get a lot of people say, oh, well, it's 57 then is our molecular ion peak. The 57 is the tallest peak, but it's not the tallest within 3 units of the peak furthest to the right. Okay? And we've got to address why we're referencing all that language here, and we'll do that here in a second. So what we're now referencing is that that's our peak furthest to the right. Okay? So now what's the tallest peak within 3 units of that? And if we're looking at this diagram, we might be like, well, it looks like they're the same height. And it looks like they're the same height as an artifact of this problem. What do I mean by that? Take a look at those lines themselves. Do those lines look different than the other lines? Yeah, why? Why are they wider lines? They're not part of the spectrum. They're drawn on by me. Okay? They're drawn on by me in Word trying to draw these lines. And I wanted to draw one of those lines slightly larger than the other. Word doesn't allow you to draw lines slightly larger than the other, particularly when they're that small. Instead, what it does, it says, oh, you must want to draw a line that's 3 times this height. No, you fucking piece of shit software. I just want it to be a little taller. Leave me alone. Okay? And it wouldn't let me do it. And so now we get stuck with this issue where there are 2 lines that are almost identical in height. So we can do a slight modification behind this. And there we go. Ta-da! Are they the same height anymore? No, they're slightly different. Which one is taller? The one slightly to the left. Okay? To figure out our molecular weight, okay, we need to find that tallest peak and now figure out where it is located. To figure out where it is located, we could now go to the axes and try and figure out the labeling behind that. So we've got 125, the next big hash mark is 130, the next one is 135, and that line is at the very next little tiny mark, which would mean 136, which should look kind of familiar because that's the number that's written up there. Because I think it's very hard to read all those numbers, I've provided that secondary numerical information on top of the graph to help you interpret. Make sense? Okay, so what does that mean for us? That means we have the molecular weight for our compound. So when this compound was run through the mass spec, we discovered that it has a mass of 136 grams per mole. Right? And now what we're going to encounter is kind of the next kind of stage behind what's going on with mass spec. What is mass spec all about? Right? It is trying to find the mass of the particle. Well, if we consider it just the mass of the particle, if I test the mass of the sample, what should I see in my spectrum? I should see a single signal for the mass of my particle. But I see a bunch of other signals. Why are there a bunch of other signals? For instance, I've got this one at 138. I also have this one and this one and this one and all of these. Why do I have all of these extra signals? Mass spec is about destruction, right? And the analogy that I typically use is a bit gruesome, and I apologize for that, right? But we could go back to old hardcore CSI stuff. If you ever watch shows where they're like, there was a bomb, and then the protagonist goes through and analyzes all the exploded patterns and says, oh, the person that made this bomb is so-and-so because there was a subtle detail of the components of the bomb piece that told us that it was made by this person. Okay? That isn't made up. They legit can do that. What they're doing is collecting all of the pieces that came out of that bomb system, and we're able to effectively reassemble to get that information. Okay? That's kind of cool. That's what's happening within mass spec. On top of which, okay, they were able to figure out that the bomb was in the mailbox, not in the car. Why? I mean, they were right next to each other. I had a mailbox right next to a car. How do I know the bomb was in the mailbox and not in the car? When the bomb explodes, if it was in the mailbox, what happens to the mailbox? Yes, Gonzo, take it a little bit further though. It explodes where? Outwards, right? The bomb is on the inside of it, explodes the pieces and curl outwards. What if the bomb's in the car parked next to it? The car explodes outwards, punching into the mailbox, pushing all the pieces inwards. So I could dissect which direction where the bomb was located based off of the explosion patterns. I can look at those pieces to decide what's going on with it. That's what's happening within mass spec. So all these individual things or peaks are parts of the exploded molecule. It's what's known as the fragmentation pattern for mass spec. It is incredibly powerful, and industry uses it a lot. Okay? The problem with it is it takes a lot of time to kind of build it through, and not enough or we don't have enough time to really evaluate that fragmentation pattern. If it is something that you find interesting, the textbook goes into some of the details behind our fragmentations. We'll address some aspects of it within the lecture theory, but as far as the lab theory, we pretty much ignore the explosion pattern. We don't look at those pieces. But we do turn and look at our molecular weight, and we'll look at this 138 thing, which takes us to the next thing in the worksheet. It says M plus 2. What is that 2 in reference to?
Isotopes.
We're looking at 136 versus 138. The difference being 2. N plus 2. Isn't M plus 2 present? In this particular spectrum, yes. What does that mean? Right? Someone cheating. Is that in a different class? We're looking at isotopes. What are we talking about with isotopes? What is an isotope?
Different amount of neutrons.
Yeah. So if I look at hydrogen, hydrogen has 3 big isotopes. We officially call them protium, deuterium, and tritium. Protium is just a single proton, so it has a mass of 1. Deuterium has a proton and a neutron, so 2 subatomic particles, so we call it deuterium for the deuce, right? We're referencing 2. And then tritium, tri, because there's 3 subatomic particles, a proton and 2 neutrons. If I ran the mass spec on a sample of hydrogen, what would I expect to see? We just said hydrogen is made up of 3 isotopes. One of a mass 1, one mass 2, one mass 3. How many signals do I expect to see in mass spec? there's 3 isotopes. I see a signal for each isotope. Turns out we only see 1. Why do I only see 1? There are absolutely 3 isotopes. What's that? Getting to the right idea, it's about abundance. If I look at a sample of hydrogen, 99.99% of the hydrogen is protium. Less than a tenth of a percent is deuterium. Less than 1,000th of a percent is tritium. Which means when I look at the mass spec, the height of those peaks is how much that sample appeared. How many things appeared of that mass. And if I look at hydrogen, almost all of it is going to be protium. I'm only going to see a signal for 1. I might get lucky in that sample and have lucked across a deuterium, in which case I'll see 99 peaks of protium and 1 tiny little blip for deuterium. But the odds that I pick up a tritium, next to nothing. Right? So the height of the signal isn't just are there isotopes, it's also how abundant or prevalent those isotopes are. Right? So does that mean I have to worry about 118 elements with 118 potential different isotopes? Right? You're not a lecturer, so I can't give you a hard time for that. No, I don't, because it's OChem, and what are we concerned about? We only care about like 10 different elements, right? So now I just have to worry about the isotope composition for 10 different elements, and it turns out hydrogen was irrelevant, right? Carbon does have an isotope effect, but it's relatively small again. The most prevalent form of carbon is carbon-12, right? We get a little bit of carbon-13, carbon-14, but if we look at the average atomic mass on the periodic table, it's about 12. Why? 99.99% of it is carbon-12, so I don't have to worry about that isotope effect. What we do have to worry about is ultimately 2 different elements, bromine and chlorine. Bromine has 2 common isotopes, bromine 79 and bromine 81. Oddly enough, separated by 2. So when we're looking for the M+2, we're trying to identify, do I have bromine? If I look at chlorine, chlorine has 2 common isotopes. Chlorine 35 and 37. Okay? So that M+2 is really saying, do we have evidence that bromine or chlorine are present? Okay? So in this case, yes, we have an M+2. Now we've got to decide, what does this information mean? Does it mean bromine is present? Does it mean chlorine is present? How would I know? That's going back to the abundance of each of those isotopes. When we look at the abundance for bromine, bromine 79 is 51% of the isotope mixture. What's the other 49?
The isotope.
81. Right? Those percent abundances, so if I grab a random sample of bromine, half of them are 79, the other half is 81, which means what do I see in the mass spec? A 1-to-1 ratio for wherever I have bromine, because they're of equal percentages. So I just have to look for the M+2 and say, are those 2 peaks about the same? Yeah, bromine's present. What about chlorine? Chlorine is roughly 75%, I'm kind of making up the numbers so I'm not 100% sure for the record, 75% chlorine 35 and 25% chlorine 37. So what you end up seeing there is a 3-to-1 ratio. Okay. All the other elements that we're concerned about don't have enough of an isotope effect that we need to worry about. So when we go through and deal with our mass spec, we're getting the molecular weight of our compound. We're now looking for that M+2, and now we draw a conclusion from it. If yes, right, we could then say it's a 1-to-1 ratio, and because it's 1-to-1, I know bromine is present. How you know it's 1-to-1? Look at the graph. We look at our M+, we said it was 136, and our M+2, 138. What's the height of those 2 signals? They're about 1-to-1. Right? That's what we're referencing, is that intensity. Right? As far as the conclusion goes, yes, I've got bromine. I could also say no chlorine, because I don't see that 3-to-1 for chlorine. Those people, well, what about 3-to-1 in the other fragmentation pattern? Don't worry about the fragmentation pattern. Just ignore it. All we care about is the M plus and our M plus 2. That's your only focus. Yes, sir.
Maybe I zoned out when you were talking about it, but how do we narrow
Easily
it down
possible.
to just bromine and chlorine?
Okay,
Just
we
those.
look for the M plus 2. Okay, so
Okay.
136 was our M plus. Do I have an M plus 2? It's 138, so yes, I do. Okay, now what we're trying to do is decide which of those 10 elements that we're responsible for in OChem have an isotope that is 2 units larger than the normal sample.
Okay, so basically we just have to memorize the isotopes for all of them?
Do you have to memorize the isotopes for all of them? No. I just told you the answer. Which ones do you have to memorize the isotopes for?
Just,
Bromine and chlorine, that's it.
okay.
The other ones, those isotopes aren't a big enough factor that we have to worry about, so you can ignore them. Okay. There are
So if there's no, if bromine and chlorine aren't present, there's gonna be an M plus 2.
true. If there's no bromine or chlorine, there will not be an M plus 2 with an intensity that matches either of those.
Okay.
Because you can see some that have very small M plus 2s. Okay? And what you're looking at there is a stacking effect for other isotopes. Okay? Being very small percentages, they do show up. They just show up in a case that's not easy enough for us to measure.
It's small enough that you just ignore it?
Yes.
Okay.
Right? For the record, because we're talking about small enough, we just ignore it. Remember how I said I drew those on there? Okay. If we delete those, what you see is something that you see like right there. Do you see those 2 peaks there? How far away are those 2 peaks? They're 2 units. That's a fragmentation pattern where what you lost was not bromine. So bromine is still connected to the molecule there, and we're seeing 2 peaks because half of the sample is bromine 79, the other half is bromine 81. Okay? Those peaks are so small, it's really hard to see and interpret, which is why I go through and draw in when there are scenarios that could potentially happen like that. Okay? So we've got a molecular weight, which we'll come back to and use. We know about bromine, we know about chlorine, we know it's a negative for chlorine. There's 2 more elements that we should be thinking about when we look at mass spec. Nitrogen has an odd bonding pattern, right? Quite literally. In its bonding pattern, it's going to generate an odd molecular weight, assuming there's an odd number of nitrogens. Okay? So if we look at our molecular ion peak at 136, okay, that's even. That would suggest I don't have an odd number of nitrogens. I could have an even number of nitrogens though, but I don't know, right? But that's a possibility. Right? Why is it all of a sudden okay when I have an even that I would have an even number of nitrogens? 1 nitrogen is odd. What happens when I take an odd and another nitrogen? What happens when you add 2 odd numbers?
Makes it even.
That's what's happening. Right? That's rare. I've seen maybe 1 instructor do that to students. I think that's a bit out there. Okay. What I stick with is if it's odd, you got a single nitrogen. If it's even, no nitrogen. Okay, so in this case, it's even. So we could make the statement. It's a bit of a stretch, but we can make the statement no nitrogen. Okay. The last thing that we can look for is iodine. And in this case, there's going to be no iodine. How do we know there's no iodine here? It's actually a bit borderline. Yeah, what's massive for iodine?
Molar mass.
Yeah, the molar mass for iodine is 127. Okay? We're at 136, so could iodine be there? Yeah, I mean, 136 is greater than 127, but then that doesn't leave a lot of room to put any other elements. Right? So if iodine is in your compound, your molar mass is genuinely huge. Like even the smallest mass is like 140, right? And that's a really, really, really simple molecule. So what we're talking about for large masses with iodine is like 200-300. If you're seeing masses in that range, iodine could be present. That could be a large contributing factor to the overall molar mass. It's also possible you just have a ton of carbons or oxygens or nitrogens. But seeing a large molar mass can be a tip-off that you have iodine. Right? The last part of that I'm a little bit less certain of is that iodine is so large that it can iodine or ionize is the word, right, to be detected by the mass spec. And that could show up as a signal at 127, where iodine is just chilling on its own. So if you're seeing a signal at 127 and you have a massive molecular weight, that's a pretty good tip off you've got iodine. Very, very rare, but it can show up. Make sense? Okay, which now takes us to the next kind of two systems. The degrees of unsaturation and the possible formula. Both of these are out of order. It makes more sense to look at the formula than it does to look at unsaturation, overarching, and then you need the formula to be able to calculate your degrees of unsaturation. So how do we calculate the formula? What is a formula? You mean E equals MC squared? Chemistry class, damn it. Formula, H2O is a formula, right? If I know the formula H2O, what other information can I pull out of that? Tons of information, but work with me here with the emphasis on the fact that we're looking at mass spec. I would know the molecular weight for water because hydrogen weighs 1. There's 2 hydrogens, so there's 2 mass from hydrogen. And I know oxygen is 16. I would know the molecular weight is 18. Sweet. Right? So the formula is related to our molar mass. Right? So what elements do you think could be in our possible formula?
Carbon, nitrogen,
Why do you think carbon and hydrogen should show up?
because that's all we do in here.
That's a fair statement. Not quite what I was looking for, but yeah, that's fair. It's an organic chemistry class. We would expect to see some carbon and hydrogen. Okay? We might also expect to see some bromine in this. Why?
Because we just found bromine in one.
We literally just analyzed the fact that bromine is present. So if we're looking at our possible formula, we would expect carbon, hydrogen, and bromine. I know the molar mass, though. So I know more than just I have those 3 elements. I can actually come up with the amount of each of those elements. Could I have 2 bromines?
No.
Why not?
79 times 2.
Bromine is 79. 2 of them would be above the molar mass. Okay? So that means of that 136, 79 of it must be bromine. What does that leave left over? 57. What's in that 57? Could it be 57 hydrogens? Why not?
Yeah.
We're going to have a hard time trying to bond 57 hydrogens together and the bromine. Right? That's just not going to happen. We're going to have octet issues. Which means it's more than likely that we're seeing more carbons than we are hydrogens. So we could start that 57 by looking at the carbons. What's the mass of carbon? 12. So how many times does carbon fit into 57? Well, we could do our long division. 12 times 4 is 48. Okay, and I'd have a remainder of 9. I don't want to do all the decimal stuff for our long division because I can't have a fraction of carbon there. Right? But that 4 now tells me I can have 4 carbons. What makes up the remaining 9? That's now our hydrogen. And because hydrogen weighs 1, I now know I have 9 hydrogens. Okay? Are there other potential formulas that could work? We have 0 evidence for any other element. Okay? So all we can do is really work within this. We tried to change bromine, it didn't work. We could try and change carbon. We can't change carbon upwards because we don't have enough to fit more than 4 carbons. But what about dropping the carbon downwards? Could I have the formula C3H, I don't know yet, bromine? Is that possible? If I drop that carbon down, that mass has to be made up for somewhere. Where does that mass need to go? To our hydrogen. So I would take 9 hydrogens plus the 12 that I just lost from the carbon, and I need 21. You're saying no. Why?
Doesn't have enough bonds for that to go.
How do you know all that? Are you just that good? You can be that good. That's fine.
I guess, because carbon can only have 4 bonds, and then bromine can only have 1. So 21 hydrogens would fit.
Fair play. I see how you're working that. Okay, I accept that. Okay. Typically, where I would go is a formula: CnH2n plus 2. What does this formula represent?
Unsaturation.
Close. That formula is a fully saturated structure. Okay, and there is a relationship to the unsaturation. Okay, and if we think about where you might have heard saturation and unsaturation before, you might have heard of it in fats, right? Saturated fats versus unsaturated fats. Right? A saturated fat is one where those are all single bonds. An unsaturated fat is where I put a double bond, at least one double bond in there. To get that one double bond in there, what did I have to remove? Do better. Do better. 2 hydrogens. We had to remove exactly 2 hydrogens to get a double bond. That number is going to become important in a second. Okay? So when we're looking at this formula, CnH2n plus 2, that's the maximum amount of hydrogens I can put on any carbon chain. So I can go back to my C4H9Br. If carbon was 4, my maximum amount of hydrogens would be 2 times 4 is plus 2, 10. I can't have more than 10 hydrogens. That was for C4. I'm actually at C3 is the one we were checking, right? Okay. So 2 times 3 is 6 plus 2. The maximum amount of hydrogens I could have would be 8. I'm trying to write 21. That ain't going to work. Okay. So that formula is invalid, which is kind of nice because now how many possible formulas are there? Just one. Okay? That's a cool system. Okay? And if we're lucky, if there's only one formula, we might find there's only a couple ways that you could possibly draw that structure out. This is one of the very, very simplest structures out there, and you will find that there are two ways I think you can draw this formula. There's only 2 options. I kind of want to say 3, but I think it's only 2. No, it's 3. I just thought of the 3rd. There's 3 possible ways you could do it. Okay? So you could immediately try and draw formulas or structures. I don't recommend that because in this particular case, that's 2/3 of your work is wrong. Okay? So let's see if something else gives us more feedback to help narrow the field so that we aren't guessing at too many different things. Make sense? Okay. So we now have a possible formula with our work behind it, and then we can also now address this degrees of unsaturation. The degrees of unsaturation typically comes through a calculation or a formula. Okay? I do not know the formula. I can probably guess it because I've now done this twice and people have had to tell me it. Your degrees of unsaturation is equal to, does anybody know it? What? You have it pulled up? So you're going to test me? 2 times the number of carbons? 2 times the number of carbons plus 2 plus the number of nitrogens minus the number of halogens or hydrogens. Yeah, X is halogens minus the number of hydrogens. And then we divide it by 2. X is our default standard for what we call halogens. It's a little bit questionable, but that's, when in doubt, that's what we're referencing, is any one of our halogens. Okay? So that is a formula that you can memorize. Okay? I will straight up say I derive it every single time I want to use it. Okay? As long as I know saturated is this formula, and I know that to make a double bond, I had to do what? Remove 2 hydrogens, I can now derive the formula. Right? It's tedious, it's obnoxious, and it takes a bunch of time. So I don't recommend that. Okay? The other option is memorizing it, and the last option is you just guess and get it right or wrong and hope for the best. Okay? So what we can now do is use that formula here. Okay, our degrees of unsaturation, 2 times the number of carbons. How many carbons do we think we have? 4, so we get 8 plus 2 plus the number of nitrogens. How many nitrogens do we think we had? Plus 0, minus the number of halogens, minus the number of hydrogens. 9 divided by 2. 8 plus 2 is 10, good job, minus 1. 9 minus 9, 0. Degrees of unsaturation is 0. What does that mean? You just calculate this random number. This was a saturated fat. This was unsaturated. The degrees of unsaturation is counting how many times you were unsaturated. Unsaturated had to do with the presence of pi bonds. So if I have 0 degrees of unsaturation, that means no pi bonds. Neat. Right? What if I have 1 degree of unsaturation? 1 pi bond. Okay? And then the nasty thing that's going to come out of this, there's an or associated with it. It isn't just pi bonds. Right? It's also rings. Because if I took a 5-membered structure, okay, 1, 2, 3, 4, or 3, 6, 7, 8, 9, 10, 11, 12 hydrogens, right? What happens if I now close that ring structure? 2, 4, 6, 8, 10. I just lost hydrogens, and in fact, I lost 2 hydrogens. Degrees of unsaturation are not just pi bonds, they're also rings. Right? I would actually argue that a pi bond is a ring. If we think back to lecture, when we talk about our rings, what rings did we talk about? Cyclohexanes, cyclopentanes, butanes, propanes. Did we talk about bianes? No, why not? What happens if I try to make a ring with 2 carbons?
It doesn't work.
It absolutely does work. It's a pi bond. It's a double bond. Right? That's why they overlap. Right? They're doing effectively the same thing. Okay? It looks weird the way I've got it drawn, but that's just a double bond. Kind of makes sense? What if you have 3 degrees of unsaturation? What does that mean? Three pi bonds? What if I had 3 rings? Wouldn't that work? Each ring is a degree of unsaturation, so 3 rings would be 3 degrees of unsaturation. So if you have lots of degrees of unsaturation, yes, it gives you some information, but it also opens up lots of possibilities too. So a degree of unsaturation is a ring or a pi bond. Right? Both of them are possible combinations. So to make it easier, 2 degrees of unsaturation could be 2 pi bonds or 2 rings, or a ring and a pi bond. Okay? So there's multiple ways you can piece it together, which is why I've never liked degrees of unsaturation, and I just don't find it to be a valuable piece of information. Okay? I do appear to be in at least a somewhat minority, so ACS does test on it, which means I feel I have to ask about it. Okay? That was 45 minutes later. Okay? So we got more information out of it than we got out of IR, so it took a little bit more time to process. Cool. But we've now fully beat the living bejesus out of our mass spec. Okay? And if we had tried to take all of this information on our work document and put it into our spectra, that would make our spectra look really messy and nasty, and again, hard to organize and think through. Again, why I preference the document. Make sense? Don't worry, only an hour.
So, if we're doing our IR, and for example, it has a peak at 2,500, and then we move to MS, do we automatically include like oxygen, for example, in our?
It's a good question. So I don't know what you're talking about with 2,500, but let's call it 1,700.
The OH 2,500.
Oh, no, I see what you're saying. So let's flip it and remove the numbers because there's
Yeah.
kind of complications. IR goes through and tells you have an oxygen, you have an OH. When you go into mass spec to calculate your formula, do you have evidence there's an oxygen?
No.
Not within the mass spec. Does your IR tell you have an oxygen?
Yeah.
If you go through and don't include that in calculating your formula, is your formula going to be correct?
No.
So what should you do? Include the oxygen when you calculate out your formula. Okay? Each of these pieces of information contribute a little bit of the puzzle. You can't entirely keep them separate. You do have to cross-communicate between each of the layers. So if IR tells you an oxygen is present, when you get to mass spec doesn't say anything about oxygen. IR is the one telling you oxygen should show up. This could be a good reason why we do IR before we do mass spec, because IR can give us some of that context about oxygens. Does that make sense? Very good question. Other questions before we try and move into the next one? Cool. Do you need a break? You want to take a break? I'm fine with that. Take a quick walk. Okay, halfway there. We got two forms of spectroscopy left. We've got our carbon NMR and our H NMR. How do we know we're looking at carbon versus hydrogen? There's a couple cheats. Sometimes the H says HNMR on it, or says an H. That's a big tip-off. The better approach is looking at the numbers at the bottom. Carbon NMR will usually run sets of 10s up to 200. Hydrogen NMR will run as factors of 1. Right? So they're looking at slightly different ranges. Same spectra, believe it or not. You're just looking at different ranges of that spectra. Okay? So carbon NMR, what do we look for? Actually, we're going to take a step a little bit back. NMR in general boils down to 4 components. Okay? You've got the number of signals, where the signals appear, the area underneath the curve of the signal, and how many times the signal breaks apart. Okay? So 4 pieces of information. Okay? Those 4 pieces of information need to get analyzed somewhat independent of each other, or I would recommend being somewhat independent of each other, and it scales in difficulty significantly. Okay? So being able to interpret your number of signals, pretty easy. Being able to interpret the amount of times your signal breaks apart, that now gets much more challenging. Okay? And can lead to confusion. So start simple and work your way up. Your number of signals is easiest addressed, or I don't know where I was going with that. Let's take a look at our carbon NMR. How many signals do we see? 4. So we go 1, 2, 3, 4. The number of signals is going to correspond to the number of unique carbons. Okay? Or if we're looking at hydrogen NMR, unique hydrogens. So what we could do on our worksheet is say our unique carbons is 4. We do have to be careful with unique as a term. That usually trips people up a little bit. So let's look at a really simple example. Okay. What I've got drawn up on the board is 3 carbons. Are they unique? Right? No. This one out here and this one out here are not unique. Okay? So if I was to look at carbon NMR, I would see 2 signals. Okay? Because this one is unique from those 2. Okay? So where this has already been addressed is when we talked about chirality, we looked for distinguishable groups. This is effectively the same thing. Okay? Can you distinguish them? They count as unique.
So you said that would be 2 groups, so for 2 signals?
Mm-hmm.
Okay. Just want to make sure.
Yep. Okay. The next part of our analysis is where do those signals show up? Okay. So what we're talking about is that we have this whole range from 0 to 200. Why are they showing up over here? Okay. Well, what this has to do with is how the instrument works. What we're studying is the nucleus of either carbon or hydrogen. Those individual nuclei are magnetic. Because they are magnetic, when we drop them into a magnet, they will align with the magnetic field. We can then knock them off of the magnetic field by hitting them with radio waves. Very, very low energy, right? But it's enough to disrupt how they see the magnetic field, and it takes them a certain amount of time to realign to the magnetic field. All of that gets monitored by our instrument, which is WIG. Right? And what that gets turned into is the signals that we see out here. Right? So if we're considering this, we're concerned about how long or short it takes to align with the magnetic field and how the radio frequency interacts with it. Well, if there's things that block the radio frequency, it's going to take a higher energy to get it to oscillate, right? Or to be knocked off balance. So we can correlate effectively-ish the radio frequency energy with the local environment of our individual atoms. Right? Said a slightly different way, what I need to do is the same thing. I'm going to see the representation. The same thing that I would do with our IR. I want to memorize particular range, that's over here, ranges and what they mean. So since I'm looking at carbon NMR, if my signals fall in the 0 to 50 range, that would suggest that those carbons are just sp3 hybridized alkanes. If I see a peak in the 160 to 200 range, that would suggest my carbon is double bonded to an oxygen. So I'm getting some structural information by looking at those ranges. Right? I oftentimes get, can you just give this to me on an exam? And I would argue no, because if you need to reference that on the exam, you burn time. That's 4 pieces of information that I think you should memorize. That's not that much. You should do that. Okay? And it will greatly enhance the speed with which you solve things. When we talk about you navigating this assignment, yes, have this handy. Look at it, reference it, because that will help you memorize it. Make sense? So if we now use that documentation with this, right, the graph says between 0 and 50 is alkane. So there's 0 to 50. Those are alkanes. This one isn't in that range. That's outside the 0 to 50. How do we want to interpret this?
That would be the carbon attached to the bromine.
Okay. I'll come back to that later, just for the record. We could go through and call our types of carbon now. We could say that there's 3 times alkanes. And if we looked at the chart, which I'd taken away, we would say 1 times, I don't know, that was in a space that wasn't labeled. That space that wasn't labeled is everything else. Tons of stuff can happen in there. depending on the immediate local environment. So we could call that a question mark. Right? The next level beyond this is why would it shift? Well, it shifts because it's closer to an electronegative element. The closer it is to an electronegative element, that element removes the electron density, exposing the nucleus to our radio waves and our magnets. Right? So what Josh suggested is that maybe that one is our carbon connected to the bromine, because I suspect I have bromine based off of my other data. That could explain why that carbon is sliding just outside of the alkane range, because it's close to an electronegative element. Right? That analysis is great. I would argue it's kind of a step beyond what is necessary for me. I would just call it 1 times x. I don't know what it is. Right? I could also get away, full disclosure, saying that's at 55. The little range was like 50-ish. Like, could I just say that's 4 alkanes? Yes. That's perfectly reasonable to do. Just like with IR, the range is a little bit different, the shape is a little bit different. There's a little bit of a fudge factor when you're looking at your types of carbons, or for that matter, the types of hydrogens. Right? Those are very loose, quick interpretations. Right? And then there were 4 things that were important for NMR. We just addressed 2 of them for our carbon NMR. And if we look at our worksheet, there's no other space to write anything for carbon NMR, because the last 2 things, due to limitations of the instrument, or really the abundance of the nuclei for carbon, we don't look at very often. Right? So the textbook will reference a slightly more advanced carbon NMR spectra. I don't think it's worth spending the time to dig into it. If you're interested in it, you can dig into the textbook a little bit. It's called DEPT. I think that's right, DEPT 40. And it adds a couple extra layers of information that can be useful. I just think there's enough in the HNMR, it's not worth the trouble. Kind of, sort of? And now we're ready for the real fun one? That's where you're all supposed to be like, yay, of course, it's the most exciting thing ever. Please keep talking. At least I'm entertained. Okay. HNMR, we asked the exact same thing. The number of unique hydrogens. So what we now need to figure out is, just like we did with carbon NMR, how many signals do we see? Okay? And I want to kind of be careful with this. I'm changing the language from the way the lecture videos are recorded. I'm referencing signals and peaks. I believe in the lecture videos, I refer to them equally as peaks. Right? And we'll see why I want to call them slightly differently as we move through this. When we looked at carbon NMR, there really wasn't a big deal. Okay? So we can look at the carbon NMR, there's 4 peaks, there's 4 signals. I don't see a difference. How many signals are in the HNMR? 4. But there's a hell of a lot more peaks. Why? Because in HNMR, the signal can split. Carbon NMR doesn't deal with that splitting. So what we need to be able to do when we look at HNMR is to be able to distinguish the difference between a signal and a set of peaks, because the signal split. Right? There are a variety of ways to go through and do that, right? And we'll look at a couple here. Right? First and foremost, what you could do is look for your integration information, which is further on within our chart, okay? But we'll come back to that. That integration information can be written as written here, 1H, 2H, 3H, 3H. There were 4 of these H things floating around. Why? 4 signals, right? But your integration doesn't have to be given to you in that format. Okay? It could be given to you, or it could be the situation where you've got something where it's not given to you at all. If it's not given to you, how do we know we have 4 signals? started us off with 4. Did you say 4 because of the integration, or do you see something else?
Oh, I see 4 signals on the NMR,
In the carbon NMR or the H NMR?
H
So why are you not saying that's a signal, 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 that's a signal? Because that's 6 signals right there. And I haven't even talked about that one, that one, that one, that one, that one, that one, or who knows what the hell's going on down there. Right? So why are you still saying 4? You may not be able to vocalize it also, but
It's like, I guess each one is a peak to represent the amount of hydrogens it's next to.
Because the first one's a proper distribution.
okay. Which you might be thinking exactly what he said, which is exactly the example that I would go through and do. Okay? We talked about using integration, looking at the sets of integration information. The next thing we could do is look at our multiplicity. I don't like starting with the multiplicity because it's harder to evaluate. Okay? But what's happening within our multiplicity is our signal splits. Okay? And what we reference there is something known as Pascal's triangle. Okay? And if we go through and look at Pascal's triangle, what's 0 plus 1? 1. What is 1 plus 0? 1. 0 plus 0? 0 and 0. What's 1 plus 0? I did it backwards, whatever. What's 1 plus 1? Thank you, I totally lost that one. That was way off. Right? And so this is something that you could do in Pascal and neat stuff. Turns out this is really relevant to NMR. Right? If I look at my signals, what this is referencing now is an intensity. There's only one signal, I'm only going to see one thing. Right? If I have 2 signals, what this is saying is the numerical value is 1 to 1, which is saying the ratio or the height of those signals is the same. So we'll get this again. You realize this doesn't look any different. Here's where it starts to kick in. Here I get 3 signals. Are they all the same intensity? Nope. The middle one is twice as high as the ones on the side. So what that's going to look like, drew that kind of horribly, is that. Then what happens? Okay? And in each of these cases, hopefully what you notice is that you're getting kind of a symmetric system behind it. That's the signal splitting out. It splits both lower and higher. Why is that important for us? If we go back and look at our diagram here, what happens with this first one? It goes up and then it comes down. That is one signal that has split into multiple pieces. How about the very first one? We look kind of carefully, and this, it's always imperfect, but we're seeing this middle set. 2 shorter, 1 in the middle. That's one set. When we move to the next set in the middle, that one's really hard to kind of piece together unless we look at the zoom in, and the zoom in makes it a little bit easier. Does that look like any one of those splitting patterns? No. What does it potentially look like? What's that? So what we're talking about is right there. That doesn't look like the splitting patterns that we're supposed to be seeing. Our splitting patterns are supposed to be symmetric. I would argue those 2 tall ones, equal intensity, look kind of like this one. Right? I would then also make the argument that this one is starting to look like one of these, where maybe it got shorter and underneath. Why am I not able to see that? How many fingers am I holding up on each hand? 2 and 3. How about now? Since you volunteered. 2 and 3, right? Okay. So now it's kind of confusing. Okay. Each of those are sets of signals. Those sets of signals separate away from each other based on their local chemical environment. But that doesn't mean they separate far enough away from each other that we can cleanly see it. What's happening here is we're getting overlapping signals, which makes it hard to interpret. Okay? This particular system, while being harder, isn't as hard as it gets because we can at least see that we have two different things aligning into it. These are significantly shorter. None of my splitting patterns are going to go short, 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 through the roof tall, and then nothing. That doesn't make sense. What makes more sense is I have overlapping signals here, which if we then go through and count, I have 4 signals, which is what Doobie was able to just recognize right away. Joshua put words to. We're looking at the symmetry behind those patterns to try and predict them. Do we always have to worry about overlapping signals? No. Sometimes it happens, sometimes it doesn't. So you need to be aware that it is an issue that could happen, but it's not a constant worry. So one of the reasons why I like going through and doing this one, because it addresses that issue. Okay? So if we go back to our summary, we have 4 unique hydrogens, because we had 4 signals. Okay? And now that sets us up with this gory, awful table that everybody doesn't like. So we got red, blue, orange, and green is a horrible color to use. Purple. So now what we want to do is start to layer in this next set of information. So within my chemical shift, what I'm trying to do is pull the information out of the graph so I can interpret it without having to worry about what's in the graph. The chemical shift is where the signal appears. Okay? So I've got my red, blue, orange, there's 2 G's in orange apparently, and purple. The red signal shows up to me about 4. The blue shows up, kind of a hard one, we'll call that 1.9. The orange we'll call 1.8, and the purple we'll call 1. Knowing the absolute values isn't critical. Right? What's important is knowing their ballpark ranges. Because then what's the next thing that we need to do? We need to identify what that range means. That means pulling back out that worksheet, thank you again, right? And saying, what does that mean for each NMR? Well, if I have stuff in the 0 to 1 range or 0 to 2 range, that's my alkanes. If I have stuff in the 6 to 8 range, that means the hydrogen's connected to an aromatic ring, a benzene. If I have a hydrogen connected to a carbonyl of an aldehyde, that shows up about 10 carboxylic acids. So I get some structural information because I know those ranges. So what I can now do is take advantage of that information and go through and provide an interpretation of what that chemical shift meant. Okay? The first part of that interpretation is insanely easy and everybody screws it up. I have a signal. What does that mean? I'll rephrase the question. I have a signal in my HNMR. What does that mean?
There's hydrogens.
I was like, I don't know what to write for an interpretation. You have a hydrogen. That's pretty important. So, hydrogen, 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 hydrogen. Where did that signal appear in that chemical shift range? If it's between 0 and 2, that hydrogen is likely bonded to carbon. Oh, it's that trash meeting that I don't need to worry about. Okay. What if it's at 4? Okay. If you haven't memorized all the ranges, that's going to be problematic. Okay. Because you happen to have the sheet in front of you. It says that shows up at 4 is everything else. I don't know what shows up there. That hydrogen is bonded to something. Could that be anything? It's a little bit mixed bag of yes and no. Why do you want to say no?
It should attach to the carbon that is attached to the bromine, because of the chemical formula.
We have a chemical formula that says we have carbon, hydrogen, and bromine. The hydrogen cannot be connected to bromine because then the structure is done, which means the hydrogen must be connected to carbon. If you want to bring that information in here, I'm okay with that. Absolutely. But what you're doing is I want you to be explicit that you're using the information from some other form of spectra to add that layer. Does that make sense? Right? And as long as you're being intentional in that action, that's okay. One of the reasons why I don't want you to do that is what if you screwed up your formula? You're now potentially screwing up your HNMR, and now everything is going to snowball out of control. So the communication between the forms of spectroscopy is the ultimate goal, but we have to be very careful and intentional about when we're going to start contaminating each of the individual spectra with our analyses. Make sense? Okay. Questions? Right, that's it for my interpretation, so I now move to the integration. The integration is the area underneath the curve. So we can go back to our spectra and say, where does our spectra give us information about the area underneath the curve? There's a variety of places to do it, and I'll show you a couple here. Okay? The first one case we'll show is exactly as it's shown on this plot. I'm going to potentially regret doing this, but it's going to happen anyway. Okay? You could see this H information written next to it. What is that saying? That's saying that's my integration. So for the red signal, my integration is 1, the blue, 2, the orange, 3, the purple, 3. Okay? That's if it's written this way. Are there other ways we can write it? Was that a question, Joshua?
Oh, yeah, if you weren't given those, how would you figure that out?
Yep. So let's go through and look at a couple other ways that this could be formatted. There we're seeing it the same. Here we're seeing a slightly different format on it. I don't see the 1H, 2H, 3H stuff anymore, but what I am seeing is this little bracket with a number underneath. What is that? That's the same thing. That's the integration information. It's given to you underneath. Right? When we consider how NMR is produced and how we run spectra, that's the default. That's how it should always be given to you. You should never see it as this H stuff, because that H stuff is now the instructor trying to give you more information than you should really have access to. You may have another question, go for it.
Are you saying that, okay, so for the one you have, is that first one going to be 3H because it follows the...
First on the right?
The first one's to the left, because for the A plus B, the N would be 3 according to Pascal's. Is that actually relevant, or is that just an example?
So that's splitting. I haven't talked about splitting. All I talked about in splitting is what's the power.
That 1 and then 2 peaks, which would indicate to the third power.
I have no idea what you're talking about.
Okay, you know how Pascal's triangle is based on A plus B to the N? That's how.
I don't know that, but okay.
Oh, I guess it's not relevant, really.
It might be the theory behind it that I don't
But
know
like,
mathematics on.
the first part is x plus y to the 0th power, then to the first power, and then that, x plus y to the 2nd power, where you FOIL, that's the 1 plus 2 plus 1. So like when you keep going, it's the
Okay.
power. But that's not, no, that's blood.
It might be applied for how we're seeing the number of signals come out of it. So I don't know how you're trying to tie that to integration. Or are you just
I was
saying?
saying, so the first one where it's 2 highs and then 2 lows, that represent the 1331, which would be
Yes.
to the 3rd power. So would that be 3H, or is that not?
Oh, snap. I and this being 1, 2, 1.
Right, that would be to the second power, so that'd be 2h. Is that accurate or no?
It totally is.
Oh, yeah?
Yeah.
Cool.
I need to do some reading on Pascal's triangle, it sounds like.
Okay, you know FOIL, the x plus y to the.
My last math class was over 20 years ago.
Oh, okay. But make sure.
So I
it's
understand what
just-
you mean.
You add two variables and then it's to the nth power, and those numbers represents each like level, because you keep doing the distributed property, is how that Pascal's triangle works.
That's really neat. I need to look into that. I really need to look into that. That actually sounds like that could explain some other things. Unfortunately, I think it is beyond the scope of what most people need in the class. But
Okay.
it does get you, because you have that better vision of it, that effectively removes the cheat formula that we'll talk about later. N plus 1 equals the number of peaks thing. Awesome observation. I need to dig into it a whole lot more than we've got time for right now. But that's actually really neat. What I was talking about is actually the integration though, not the number of peaks. We'll get to the number of peaks and we'll go through something that if you know maths, maybe you should talk to him a little bit better, a little bit more on it. Otherwise, I've got a cheat formula system that doesn't involve knowing where Pascal's triangle is coming from. But my interest is now very, very much peaked. I'm very curious. So, integration information underneath 2, 3. Right? That is how it is typically given. So if we go through and look at these, you'll see a bunch of the numbers kind of next to it. Sorry, and we're seeing complex splitting patterns here, which is, I'm now trying to wrap what you were telling me around that. Yeah, different argument. Sorry. Underneath, all written out. A couple people got confused by the comma. Why is there a comma there? Because this isn't 43. This integrates to 4. This signal integrates to 3. I'm just trying to make sure that people see that as separate signals. That's the intent. Does that make sense? And then when we get to real spectra, which they're going to go sideways on us. I guess I could rotate it. Now it's upside down. We go to real spectra, you'll see the numbers written underneath with brackets. Right? How hard is it to get that data? Incredibly easy. When you run the spectra, you click a button that says integrate. It's done. Like that's how incredibly fast this is. How long have we had that technology? 80 years. NMR itself, HNMR is maybe 85 years old. So being able to pull integration information off, we've known for a long time and we've had the computer ability to do it. Okay, why am I mentioning it and getting mildly irritated about it? Okay, kind of back to Joshua's question about how is the integration information going to be given to us. It can be given to you underneath. It can also be given to you, okay, as that H thing, because that's how I'll give it to you. And then you will also get something like this. For this particular one is a nice easy one to do it for. You'll be given that and expected to interpret. How do we interpret the integration information there? Is it given to you? What is integration?
Calculus.
What does it mean to integrate? It's the area under the curve. Which means when we're integrating, we're just saying how much space is underneath that. So for this particular one, we would say the integration was 1 to 1. They're both roughly the same area underneath the curve. We wouldn't be able to tell a difference between them. Okay? And ACS expects you to do that. I've got problems with that. Okay? Number one, because it's bloody easy, the instruments are incredibly easy to generate that data. Like, we don't need to make students be making approximations. But if we move to something like this, what's your integration? You might be able to go through and say, these are 1-to-1. Those are about the same height. Okay? But these other ones are significantly taller. Well, how much taller are they? Well, if I get out a ruler and take that, and then I go that, and then I go that, and then I go that, right? I could now go through and say the height of those, okay, would be 3-to-1 for this one, maybe. But this next one is even taller still. Right? What's the difference? Because if we go through and actually look at what the screen showed, those were 2s and those were 3s. Are those the same height? No. Why are they both integrating to the same thing? Here's a peak, right? There's the width of my peak. What happens if I do the integration but I want a wider peak? What has to happen to my peak height?
It's lower.
And if ACS is asking you to interpret based off of height, which one of those integrates to more? Everybody's going to say this one. But we aren't factoring in the peak width at the same time. That's incredibly challenging to visually see. And I would argue it is absolutely moronic. I'm being recorded, and ACS deserves to get yelled at for this, to expect students to pick that up, particularly when we've had the technology that tells us the integration within seconds, with a button click. It's not even like you have to run any fancy calculation. You just click a button and the instrument spits it out. Okay? So you are responsible on the ACS final exam for approximating your integrations based off of peak heights. It sucks. I apologize. It's the way it is. For the sake of this assignment and any exam that I give you, you should always have the integration information provided in some form or another. It can be written out as these H's. It can also be written out as the numbers underneath.
So on the exam, are you gonna give us like a little chart with this?
This is a nice follow-up question. I can tell you're a little distracted and not talking about that, but that's okay. Right? It's definitely all good. Don't worry about it. Yes, on the exam, I will give you the spectrum document. Right? It doesn't, to me, it doesn't have any actual information on it, but it does at least provide a logical flow that I think is useful. So it will be on the exam. Okay, now I did my mild rant. I'm going to call it mild. Let's deal with our color patterns here. We started red here. Blue was those. Orange. And purple. Okay? What does it mean for the integration? Okay? The integration is effectively the count. So when I go through, because now we're looking at HNMR, HNMR counts every single hydrogen. One of the benefits of HNMR is the hydrogen nucleus, protium, is nuclear or magnetically active. For carbon, carbon-12, the most common isotope, is not magnetically active. So when we're looking at carbon NMR, what we're looking at is carbon-13, not carbon-12. And because it's less abundant, we can't guarantee that when we see a carbon-13, that we're seeing the same carbon-13 in any individual molecule. So it's really hard to nail down a ratio of where they're all coming from. That's our integration. For HNMR, because 99.99% of it is the same thing, it's just going to count all of the hydrogens. So if I go through and see, our instrument sees this hydrogen, where would I predict that hydrogen to appear in my HNMR? Between 0 and 2, good guess, yeah. Okay, it'll probably show up around, officially about 0.9. Okay, you don't need to know the exact value, okay, but about 0.9. So the instrument sees this hydrogen and goes, ta-da, hydrogen. There's a signal. Instrument sees this hydrogen. Is this hydrogen unique from this one?
Nope.
Nope, so where does it show up?
It's just lost.
Ta-da, another hydrogen. Sees this one. Where does it show up? It sees this one.
Goes in the same spot because it's not a unique carbon.
Internal mirror plane, these hydrogens are identical to those hydrogens, which means it's also going to show up in the same spot. So we got 1, 2, 3, 4, 5, 6, right? Okay. Where does this hydrogen show up?
Somewhere else.
Somewhere else. It's not the same as these, because that's a CH2 versus CH3. Where it's going to show up is about 1.3, I think. Don't stress about the details. So it's going to count that. Then it's going to see that one. Where's it going to count that? Same spot. Okay. What happens now is that when we consider, and I'm going to have to erase the structure to clean this up just a little bit. Theoretically, it's not going to slope it like that. Okay. But when we test this, we're not testing a single molecule, we're testing hundreds of thousands of these. Okay? Which means this is going to continue to grow, and so will this one. Okay? And at the end of the experiment, when we ask for the integration, what it's going to do is look at the area underneath that curve, and it's going to say that this is, I need to erase that, 2, okay, or rather, yeah, we'll call it 2, 1, 2, 3, 4, 5, 6, and this is 6. What does that 2 and 6 mean? The number of hydrogens it counted. Where did it count those hydrogens, though? Not across a single molecule, but thousands of molecules. So when we say 2 and 6, this is likely 2,000 and 6,000. Does that mean there's 6,000 hydrogens on my molecule? No, it just means when I test 1,000 molecules, there are 6,000 hydrogens like that. So really all the NMR can tell us is the ratio. For every one of these, I get 3 of these. That could mean in my structure, I have 3 and 1. Right? So my structure could be something like this. Right? 3 hydrogens all identical, 1 hydrogen different from it. Is that what we use to generate this? No. Isn't this going to generate the same plot? Yeah. And that becomes the problem with integration. Integration only sets you up with the ratio. It's not the number of hydrogens. So we have to be real careful on that. Right? Why is that so challenging to understand and manipulate? What is 3 plus 3 plus 2 plus 1? How many hydrogens in this compound? 9. What did the ratio turn out to be? The exact answer. So the number of times that it turns out to be the exact answer is frequent enough that we start to fall in the trap saying integration is the number of hydrogens. Right? It's not the number of hydrogens, it's the ratio. Be very careful with that, because you can encounter cases where you have symmetry. This didn't have any symmetry, but the first one I drew did have symmetry. that symmetry limits or changes some of those ratios around. Right? So symmetry will almost always be the bane of your existence. You've got to watch out for it. Make sense? Ish? Okay, so we've got our numbers. What does that mean? If I have an integration of 1, what's my easiest interpretation? If you flip it, I'm all on board. H, I'm still holding to my original interpretation. It's H bonded to something. Now you're changing it to C as opposed to question mark. Why do you want to change it to C? Chemical shift still puts it in question mark, so I don't accept that. I would argue it's the same reason that Joshua wanted me to put a C initially. We've referenced the formula enough that you're like, I know it's got to be carbons. Okay? I understand that. That's okay. You can make that shift to a C. Perfectly acceptable in this case. Again, I would lean more towards the question mark because I still don't know for certain. Okay? And we will encounter a case where that question mark becomes fully resolved within HNMR. Sometimes it won't fully resolve and we have to use the chemical formula. Okay? How about the bottom one? I've got 3 hydrogens. What should that interpret to? CH3. Okay? And you'll note that what I'm introducing now is a hanging bond for that carbon. Because that hanging bond means I need something there. I don't know what it is yet, but what I'm trying to call attention to is that there's something that's missing out there that I need to eventually fill in. Kind of makes sense? It's a little bit bigger. Okay? Is there another interpretation? The answer is yes. What's the other interpretation? What's that? Is this 3 hydrogens bonded to a carbon? Yeah. This satisfies that interpretation. If I have an integration of 3, I just have 3 HC bonds. This is a perfectly valid interpretation. Why do we not want this interpretation?
Doesn't really tell us.
It does actually tell us stuff.
Well, it's the same as what we had before we did the integration.
Oh, it means I have 3 of them. I would actually say it's more than that. We start to, and it's not the carbon NMR necessarily, it's going to be our molecular formula. Okay? This says for that one signal I have 3 carbons. Not only do I have 3 carbons, all 3 carbons must be identical to each other because the hydrogens have to be identical. Which means in my formula of C4H9Br, I can only have 1 more carbon to explain 3 more signals. And the other 3 hydrogens have to be identical to each other. The odds that I get that much symmetry in my molecule are slim to none. It can happen, but it's rare. For instance, here, how many carbons did I get? 2. How many carbons do I get? 1. But there's 6 carbons there. There's so much symmetry within this molecule that all those carbons become identical to. So I can encounter situations where I get tons and tons of symmetry. It's just less likely and it's harder to manipulate. You now have a whole lot more pieces floating around. So when you're going through and doing your integration interpretation, try and pick the simplest interpretation possible. It is easier to have 3 hydrogens all bonded to 1 carbon than to have 3 carbons all with 1 hydrogen connected to them. Does that make sense? So what's the next interpretation? CH3. What's the next interpretation? Okay. That right there, particularly in combination with your formula, is enough to figure out the answer. Okay. That sets you up that there's only one option that you can possibly manage to get you your correct answer. That's it. Okay? So you could solve it, and I'm okay with that. Okay? But for the sake of this assignment, you're also getting graded on your multiplicity interpretation, which means you have to navigate through that also. Okay? On an exam where all you need is a structure, okay, jump straight to the answer if you can. Okay? That's assuming multiple choice. Show your work, you got to show your work all the way through. So let's push into the hell that is multiplicity. The multiplicity is now the number of peaks. So let's take a look at the red signal. The red signal is probably the easiest of these because we've got a zoom in of it, but we can go through and now count the number of peaks. How many peaks do we have? 1, 2, 3, 4, 5, 6. We got 6. Okay. For your own kind of practice, what you could also do would be to look at that signal down there and be like, do I agree and see 6 peaks? Theoretically, you should hit 6 peaks. Okay, so you should be able to look at the actual digital image to be like, yep, that's 6 peaks. I do think that's hard, which is why I provided a zoom in. Does that make sense? Let's move to the next easiest one, still challenging, or slightly more challenging. Let's look at the purple one. How many peaks? Doobie and Joshua, keep your mouth shut. What's that? 3, okay. Fine. Okay. Very often I'll get people going through and saying, but isn't that right there a peak, and then 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 a peak? And I can totally see what they're trying to get at. They see kind of those shoulders behind it. And when you go through and look at some of our spectra look very much like that. So when you're looking at the digital spectra, which is the most common thing that you'll look at, what you should try and do is find some other way to visualize it other than looking for those tiny little pinprick black points. What you can look for instead is the white space in between those pinpricks. If you only have 1 peak, there's no white space in between. If you have 2 peaks, there's white space in between. There's 1 white space. 3 peaks gets you 2 white spaces. Kind of, sort of? So now when we go through and look at that 3H signal, our purple one, and we look real carefully for the white space, okay, we're seeing a white space that would go all the way out. We're seeing a white space that would go all the way out. That's 2 white spaces. The only scenario that I get 2 white spaces is where I have 3 peaks. Make sense? Cool. Orange. Aren't you glad there's only 1 hour left? How many peaks for the orange signal? No. And sorry, Dewey, Joshua, you can speak up again. Ah, so we have overlapping signals, and that's where we have to decide how those overlapping signals come into play. give you 5.
Oh, I thought it was
Oh, my bad. Then yeah, I'll give you that. So blue, a 5. Okay, that one I would argue is the harder one. The orange one is why I picked orange, because I think it's a little bit easier. And that orange one, those 2 tall peaks are really, really tall and standing out. That's like the 2 peaks that we had here. Okay, they stand out away from each other. That's getting us our 2 peaks. Okay, why 5? Okay, so for the blue one, we're trying to again match this patterning that we've drawn out here. Okay, remember, it has to be symmetric. It has to drop back down on the other end. So far, all we've done is go up, which means minimally we have to match that going down. And that match would be underneath the orange, which is why we can't see those peaks. A little bit easier to see, Jazz? Okay. Why don't you say 6 peaks? And you're saying I'd see that extra little shoulder out there?
Because it's even.
6 peaks is still even.
Well, no, I mean, it's because it's 2-ish, you have an odd number of peaks within the signal.
Well, it's 5 versus 6. 6 is even.
Yeah, because 2 is even, you have the odd now.
False connection.
No.
False connection. I can draw a structure that has an integration of 2h that has 6 peaks.
It would just show an extra peak, right? Like a dimension.
I mean, theoretically, we would see that extra peak. What am I trying to point to with my blue arrow out here? There's that extra peak. How tiny is that extra peak when we had 6 peaks? It's pretty small, isn't it? Do you think that extra peak could fit in that space?
Probably not, no.
It's really just a question, right? Some of that's just going to come kind of with experience behind it. To me, I'd be hesitant to say that there isn't that extra signal, because the width that I see for those 2 tall ones, those are pretty big. So those could encompass, and that's why this side is bleeding a little bit instead of going straight up. It's bleeding. Maybe it's bleeding a little bit because there's another peak hiding in there, and that's what's causing that bleed. Okay. So for me, I would be nervous saying as it was just 5 peaks. Okay. So what I would recommend is not saying 5 or 6, because I don't really know. I know at a minimum it must be 5. There's no way it could be 4, because that wouldn't be symmetric. So for me, what I would interpret here is 5 plus question mark. And depending on how confident I was in that 5, I might maybe even put an X through the question mark, being like, nah, I think I like the 5. I'm going to stick with that 5. But the reason I want to put that question mark is what happens when I try to put together all the pieces. If it doesn't fit, I did something wrong. I now have a very good place that I could start looking for what I did wrong, because I don't trust my analysis there. Right? You are absolutely okay to say, I don't trust myself. Note it. That gives you a way to cycle back and check your work. Right? Which then sets us up with the interpretation, or almost the interpretation of it, kind of a middle ground interpretation. This is the neighbors, and this is the formula stuff that you were dropping with your powers that I would say we just memorize as a different formula system. Okay? We have to figure out our neighbors. Okay? There's a formula. Neighbors plus 1 equals the number of peaks. Okay? So what does that mean for us? Multiplicity, this was the number of peaks. This is my neighbors. Peaks plus 1 equals my number of neighbors. Whoops. Try the math. Peaks minus 1, I can do math. Because it was neighbors plus 1 equals peaks, right? So if I have 6 peaks, how many neighbors? If I have 5 peaks, I have 4 neighbors plus question mark. 2 peaks. 1 neighbor, 3 peaks. Okay. Now I've interpreted the neighbors. Right? Well, what is a neighbor? Are we neighbors? You kind of shook your head no. You don't think we're neighbors? I'm not trying to be a trick question. What does it mean to have neighbors? Okay, you're living next to them, right? Right. So why did none of you say that I'm your neighbor? Don't we live in the same valley? Yeah, does that count as a neighbor? Right. What would count as your neighbor? Okay, same block. Okay, what about the next block over? So they're not neighbors? Okay, so it's going to come to a definition. Okay, and that definition is ultimately coming down to what the effect is. Why are you referencing your neighbors as the ones in the block? Do you interact with them? You don't interact with the ones in the next block over. Okay? Which is interesting. You must be very, very social. Nobody has ever sat within the block. Or you live on a very, very short street. Most people are like, oh, it's the house next door to me. Okay? Yeah, the house next door, okay, neighbors. Okay? The apartment underneath me, neighbors. Okay? But 2 apartments down, those aren't neighbors. 2 houses down, those aren't neighbors. Okay? Because they're not immediately next to me. And so ultimately, that's a decision that we make when we think about neighbors. Neighbors in this case isn't a decision we make, it's a decision that the molecule makes for us. And the rule that we have to abide by as neighbors is within 3 bonds. Right? So we've got a drawing up here. So what we want to do is take a look at 3 neighbors, or 3 bonds. So we'll start with this first one. I want to count within 3 bonds. So there's 1 bond. There's a second bond. Is that a hydrogen? Yes. Is that a neighbor? Why not?
It's all the same carbon. That's what I say.
Which is fair. And we can run the same house argument too. But this is where I want to throw a counterexample. Are those neighbors?
Yeah.
Why are you now saying they're neighbors? Because he's saying they're in the same house. They aren't neighbors. What's different about this structure than this one? What's special about pi bonds?
Takes away hydrogen.
Fair? Keep going.
Locks it into the same plane.
Locks it into the same plane, ultimately saying pi bonds cannot rotate. This hydrogen sees a CH3. What does this hydrogen see? Another hydrogen. Are those hydrogens chemically different from each other?
Yes.
Yeah. They may be in the same house. They're neighbors. Right? So we have to be real careful about saying they're connected to the different atoms. Right? So, and that's why I asked this. Okay? Are you still right? Are they neighbors? No. Okay? But it's not because they're connected to the same carbon. It's because they're chemically indistinguishable. So it goes all the way back. Can I distinguish between them? Are they unique? They are not unique. I would confuse them for each other. Okay? So they are not neighbors to each other. How about when I go the other way? 1, 2, I'm at carbon. That doesn't count as a neighbor. 3, is that a neighbor? That is chemically distinct from this one. So this one counts as a neighbor. It's within 3 bonds. 1, 2, 3. Yeah, that's a neighbor. We'll get some people saying, but isn't it the same as this one? Should I count it? All right, well, think about the house next to you. Does it have more than one person in it? Okay, yeah. Do you have the same relationship with each of those people? Slightly different. Okay, they share a house, so they may have similar tendencies and you may have similar activities, but you're going to interact with them slightly differently. You have to count both of them. So this hydrogen sees 2 neighbors. What if I went 1, 2, 3, I'm going to have to add a bromine out here, 4? Is that a neighbor? What's the rule? Within 3 bonds. Is that within 3 bonds? That was 4 bonds. That's not within 3 bonds, which means not a neighbor. Kinda, sorta? Okay, so what does that mean for us when we start to move into our interpretations? The easiest one to look at is going to be this one right here. So we'll look at orange. My first interpretation, I want to copy the past stuff. So I've got a CH3. Okay. That CH3 is bonded to something. The next thing it's bonded to has to have 1 hydrogen connected to it. So there has to be something out here. Okay. If I make it a hydrogen, why is that problematic? If I draw a hydrogen right here,
Would make sense.
it closes the structure. I wouldn't be able to continue out. And it would be an identical hydrogen, so that doesn't work. So there has to be an intermediary atom. Fun discovery about neighbors. Okay? We only know we have neighbors because we can see that they're there. What if we lived next to people that had 30-foot fences? We would never know if they were neighbors or not. Okay? That 30-foot fence analogy is oxygen and nitrogen. Oxygen and nitrogen will hide neighbors. Why is that important for us? We know the identity of the next atom then. It must be a carbon. And I know that carbon must have 1 hydrogen connected to it. I want to continue to show my hanging bonds. That new carbon is not being addressed within this line. Okay? I'm guessing at it effectively based off of the data of my multiplicity. Kind of, sort of? Okay. So what happens? Let's move to the other CH3. Copy over CH3. It has 2 neighbors. That means whatever it's connected to must be a carbon, and I want that carbon to have 2 hydrogens. Hanging bond. Okay. Let's do the very first one. I have H bonded to question mark. Is it a question mark anymore? Why not? It has neighbors. If it was oxygen or nitrogen, I wouldn't see any neighbors, which means that hydrogen must be bonded to carbon now. I don't get a choice. This is nice because I get corroborating evidence. The molecular formula and the NMR are suggesting that that's carbon. That's good. I like that. Okay. I need to be next to 5 neighbors, which means I need to be bonded to a carbon, and that carbon has to have 5 hydrogens. Can it do that?
No.
Why not? Octet. I can't bond 5 hydrogens to that carbon. How many hydrogens could I bond to that carbon?
3.
3 is a reasonable guess. But now I only have 3 neighbors. So what has to happen? I need another carbon. That other carbon also is connected with my 2 hydrogens, and I still get that hanging bond. Kind of, sort of? Okay. What happens here? The next one, I had a CH2. And I need 4 neighbors. How do I get 4 neighbors? Okay. That's not 4 neighbors.
Another carbon.
Anybody have another idea? How about 2 CH2s? 2 CH2s would work, right? That's still 4 hydrogens. How do I know which one's better? Who's right? Doobie or me? Where's your confidence, Doobie?
Oh, yeah, I am, but. I guess, I'm right from the,
With the chemical shifts.
yeah.
Right. Well, there's a-
Chemical shift isn't going to be much of a difference.
Oh, it's-
Would it be because of the multiplicity, because, or integration, because that means if there's 2 CH2s, they would be the same.
They wouldn't necessarily be the same, but if I run that CH2, remember this is that middle CH2, and I say CH2, CH2, what do I expect to see in the rest of my spectra? 2 more CH2s. Do I have 2 more CH2s? I do not, which means I'm wrong. Well, dang, is Doobie right? Doobie said I've got a CH2, yes, that's bonded to a CH3 and a CH. Do you have a CH3 and a CH? Ah, okay. So your breakdown is internally consistent where mine failed. Make sense? Okay. What we have now just done is 80% of the question. Okay? As exciting or depressing as that may be. Right? Because what we have now processed through is all forms of spectroscopy. Everything written out would get you full credit. The last part is now putting all the pieces together. Okay? As I said kind of already, you could have figured out the answer without looking at all the multiplicity, but I want to look at the multiplicity. Let's look at the hard way to do this. Okay? If we summarized our interpretations here, down here, would we have a problem? How many carbons have we identified here? A lot more than 4, which what does that mean?
Gotta combine some of them.
I've got to combine some. I've duplicated content. Right? So now what I can go through and do is look at those pieces and be like, well, where did I duplicate? Where did I duplicate? And in deciding that duplication process, I typically start with the ends, so CH3s. Right? So I'll start at the bottom here and say, as a summary of a piece, I have a CH3 bonded to a CH2, right? Was that one? Yeah. Okay, so all I'm doing is summarizing that piece down there. Could that CH3 be the same as the CH3 identified in the previous step? Well, Jazz was like, yep, I agree, yep, it could be the same, and then you went, what's the
That, the fact that the purple has more hydrogen, one more hydrogen than the orange one, like in this.
As I, this CH3 is next to a CH, this CH3 is next to a CH2, which means those two CH3s are not duplications. So what I could try and do then is say, okay, I'm going to draw that one. Anybody unhappy with what I just did there? Okay, Doobie, since you're not unhappy with it, what did I do?
You drew the second, the blue one, just not one correct.
No, I drew this one.
You drew for this, that one.
But this says CH3CH, this says CH3. What did I do? I flipped it.
Oh,
Why I flipped it, magic. But the hope is that that flip might help us later on. Okay, which you don't necessarily know, so arguably we shouldn't flip it until we need to think about that. Okay, so now we could go back up to either the blue or the red. Doobie, you said blue, so let's take a look at the blue. The blue has a CH3. Ooh, okay. So the blue could be duplicated with one of those pieces. That CH3 is connected to a CH2. Do I have a CH3 connected to a CH2? Yeah, so the blue could be duplicating with, which one was it? The purple, okay? But the blue has an extra piece. The blue has an extra piece saying I have a CH. So what do I need to do? I need to add that CH. Okay? Make sense? We're now trying to maintain internal consistency. My CH3 still has a CH2 next to it, okay? But I don't know what's next to that CH2. Blue tells me my CH2 is next to a CH3 and a CH. So it's added a little bit more information. We've removed some duplication. All right? What about red? What's going on in red? What do I have? That one's super tiny to see. I have a CH3, right? Next to a CH. Do I have a CH3 next to a CH? Ooh, I do. Okay, so that is duplication with my orange one, except I have this extra CH2 I need to include. Yeah? So what we've now done is removed some duplicates. We've simplified this. Are we ready to put it together yet? How many carbons do we have in my summary? 6. How many am I supposed to have? 4. Can't put it together yet because I have too many carbons, which means there's still duplication. Okay? I don't need to look at my HNMR now. I have to look down here and say, where do I have duplication? Okay, we've addressed the hell out of the CH3s, which means we need to navigate to something else. Okay, how about the CH? I know my CH is next to a CH2 and next to a CH3. Do I have a CH up here? I do. It's next to a CH2, and I don't know what it's next to. If these two were duplicates, this would need to be my CH3, right? But if that's the case, these two need to be duplicates. Well, that CH2 is next to a CH, that CH2 is next to a CH. What does that mean? These are duplicates, these are duplicates. I can take that information, I should have written that there. Am I on the screen? I got that. How many carbons? 4. How many hydrogens? 9. But this is a problem. I'm missing something.
Where's that bromine?
Oh, that's right. Back in my chemical formula, I had a bromine. Bromine has only one bond left. So now I could say my final structure is that carbon chain with a bromine in the middle of it. And I now have a final answer where all the pieces internally corroborate each other. Yay, exciting? And that only took us a whopping 129 minutes, or is that an hour and 29 minutes?
It's something. 129 minutes is 2 hours.
Then the numbers are actually so large that I can't read them in the recording. So I'm gonna just try and stop the recording and hopefully not break